I'm Anup Patel from Ventana Mico. I'll be showing a nested virtualization acceleration demo. Before I proceed, I'll give a quick recap of the nested virtualization, how it works in RISC-V world. So last year there was a talk about this in the summit. So this is the logical view of a nested virtualization in RISC-V world, where we have three distinct worlds. Where is the host world, which is the native world, where you have a host hypervisor or L0 hypervisor running, and then you have a guest world where you have another hypervisor running inside a host hypervisor, and that hypervisor creates another world which is the nested world or the L2, where you have some other operating system or Linux kernel or something else running. And this can theoretically go on, but for simplicity we have kept it shown all three layers only. And we don't expect, or this does not expect any special hardware support in RISC-V. We essentially multiplex the existing VS and VU modes and create this nesting of layers actually. So the process of virtualizing or achieving nested virtualization requires that the host hypervisor emulates the H extension functionality for the guest hypervisor, which means that the host hypervisor will be emulating the H CSRs, VS CSRs, and various H instructions, H fancies, and all those things. And the figure over here or the diagram over shows that whenever the guest world accesses the H CSRs or H instructions, it will trap to the L0 hypervisor, and the L0 hypervisor will trap and emulate the whole thing. And similarly, when the guest hypervisor or the L1 wants to enter the nested world, which is L2, it will have to go through the L0 hypervisor, and this is achieved by doing lazy trapping of the SRAT instruction. And whenever there is a lazy trapping or there is a world switch through the L0 hypervisor, there is a nested switch involved, where the nested switch switches the guest world from non-nested case to nested virtualized case. So this is the vanilla nested virtualization, how it works in RISC-V world, but we want to now accelerate this whole thing. So our approach is that we use a collaborative approach where the guest hypervisor and the host hypervisor will collaboratively minimize the traps that host hypervisor has to process. And we do this by having a shared memory interface between the host hypervisor and the guest hypervisor. Essentially, the guest hypervisor will set up a shared memory on each virtual CPU at boot time, and then use this shared memory to club the CSR access and the H instruction accesses basically. And we have designed this SBI NACL extension which achieves this functionality, and it's a modular, the extension itself is modular, where it's defined in terms of optional features, and it's up to the implementation that the level of acceleration it wants to do. And this is the demo setup that I'll be showing next, where I have two separate hypervisors. The L0 hypervisor is XVisor, and the L1 hypervisor is KVM, and I'll be running a regular Linux as a nested world. Okay, so let's move to the demo. So what we'll do first is that we'll create a QEMU instance, which is our host or the actual hardware, where we'll run XVisor. So BIOS is of course the M mode is the OpenSBI, kernel is the XVisor, and initrd is the XVisor disk, the disk containing the guest images, the guest L1 images basically. So you can see it just booted host hypervisor, and we'll see, just for simplicity I have just kept one core so that we can compare the traps and all those things. So as you can see, there is the single guest with just one vCPU. And to start with, I have disabled acceleration so that I can show you the amount of traps are there without acceleration. And now we'll attach a disk to the guest and then boot the L1 guest. So now L1 is booting. So we are first booting KVM inside the XVisor. And again, the VM is also having just one CPU, vCPU. Yeah. Now we'll actually mount the XVisor disk or the L0 disk in L1 so that we can reuse the same kernel images to run inside nested guest. And now we'll probe the KVM module. Yeah. So the KVM is initialized. So again, you can see that there is no acceleration at this point. Yeah. This is vanilla nested virtualization. This is in order to compare with the acceleration case, which will be demoed after this. Yeah. And now we launch the VM, the KVM VM inside XVisor VM, and we do this using KVM tool, of course. So at this point, what you see is a nested guest booting. So a Linux is booting as a nested guest or L2 level, and you have two layers running above it. So this is being virtualized by the KVM running as L1, and the both things are combined running inside L0, which is Hypervisor. So it is three layers running separately. As you can see, it's much slower compared to the L1 because now you have several traps being, and the L0 hypervisor is actually functionally emulating the H extension for the KVM. It is emulating all the HCSRs, fancies, and everything basically. Yeah. So at this point, the nested guest has booted. So we'll simply see that it's also just a single core thing for the sake of demo. And now we'll see the amount of traps that went in to reaching this point actually. So Hypervisor has this command to show the stats of the number of traps obtained. So these are the set of traps it processed while the nested gets booted. So now what we will do is basically recreate the same virtual machine or the same setup with acceleration enabled in Hypervisor. So we destroy and recreate the VM and ensure that the nested acceleration is enabled. Yeah, so as you can see, we recreated the VM, and now we have ensured that the nested acceleration is not disabled. So we do the same process. We attach the Hypervisor disk to the VM so that we can reuse the same L1 images for the L2 as well, right? So we start it again as well. So now L1 is booted again, but now it's booted with acceleration. So and you will see that when the KVM module is probed, you will see a different message that acceleration is available. No change in the guest configuration or L1 configuration, just single core at this point for apple to apple comparison. Yeah. We mount the Hypervisor disk in the guest to reuse the images to create L2. So this is inside L1 right now. And now we are going to probe the KVM module. So interestingly, you will see a new print message that KVM, this SBI based nested acceleration is available, right? Because Hypervisor we have enabled the acceleration part now. And now we start the same L2 guest again with acceleration, and you will see the difference. So it's faster than before, and you will see that the boot time has reduced. And when we dump the stats and compare the stats, you will see a lot of traps have almost negligible now. So yeah, so it has booted, and we'll simply just show the configuration of the nested guest. So this is L2 right now, we're running with acceleration. Yeah, and now we show the stats. Okay, so and before looking at that, we'll just quickly go back the old stat that we just printed. So you can look at the boot time, it was just roughly 19 seconds. It's quite less compared to the previous when we booted the nested guest. Right, so it was almost 28 seconds. Again, this is all running in QEMU, so on the real hardware you will see much more benefits. So these are the stats in the non-accelerated case. You see there were a huge amount of traps. Particularly you can look at the HS mode CSR accesses. These are really huge. These are all the HCSR accesses. And you can see the fences, there are quite large number of fences going on. And now you compare these stats with the accelerated case. See, we have almost negligible HS mode CSR traps. And we also have negligible H fences now, because all this has been batched through a shared memory and clubbed into a nested world switch. Yeah, that's all for this demo. And if you have question, please reach out to me separately. Thank you very much for attending this.